Hello, everyone. I am Sam Hansen,
And I'm Sadie Witkowski.
and you are listening to Carry the Two, a podcast from the Institute for Mathematical and Statistical Innovation, aka IMSI.
The podcast where Sam and I talk about the real-world applications of mathematical and statistical research.
Sadie, it's wonderful to see you and to be recording with you again. It has been too long.
It absolutely has. I'm so glad to be back. Though, while it is good to see you, I doubt you had me come down here just to exchange pleasantries.
Too true, this is Carry the Two, after all, not small talk hour.
Exactly. And as it is Carry the Two, what application of mathematical and statistical research do you want to share with me this time?
Well, in this season of Carry the Two, we are going to be examining how math and stats is helping scientists, engineers, and industry develop new and emerging technologies.
Ooh, what sort of technologies are we talking about? Are we going to go Iron Man on our listeners?
Not exactly, especially as these technologies aren't fiction. They are real. And I'm talking about everything from materials development to computational medicine to fusion.
Amazing. And will we be focusing on any of those today?
Nope. Today we're going to be focusing on quantum computing and information.
Quantum computers. Feel like they've been emerging as a technology for quite a while now.
That they do, and for good reason. It was back in the 80s when the theoretical underpinnings of quantum computing was first laid out by luminaries like Paul Benioff, Yuri Manin, and Richard Feynman. And then through the 80s and 90s, yet more names like David Deutsch, Peter Shor, and Michel Mosca developed mathematical algorithms that could leverage quantum computing architectures to work faster than any traditional computers.
The 80s. We've been talking about quantum computers for 40 years now? And is it still an emerging technology?
I'm going to have to take a second here and put together my brain that the 80s were 40 years ago. But to be fair, Ada Lovelace and Charles Babbage started laying out the theoretical underpinnings of programmable computation in the 1820s. Then Turing put forth his formal mathematical model for computing in the 1930s. And finally, in the 1940s, machines that we would recognize as the progenitors of our modern computers started to show up.
Not to mention how Babbage and Lovelace were influenced by mechanical calculators for arithmetic that were first created in the 1600s, and how those calculators were extensions of the abacus, which has been around since, I think the 3rd century BCE. Okay, so I guess 40 years isn't that bad.
And it's not like there are no quantum computers out there at all. In fact, the first proof of concept came in 1998, and there are a bunch of companies out there that are currently working in the quantum computing space. Some you have heard of, like IBM and Google, and others that are not yet household names, like D-Wave and Xanadu.
I guess my question is then, if we know how to build quantum computers, and we already know of algorithms to use with them, and mathematics that they can speed up, what exactly is the holdup?
There are many different answers to this question, from how expensive and hard it is to construct the physical systems called qubits that are at the heart of quantum computing, to the need to continue to develop the theoretical and mathematical underpinnings of the field. But those aren't what I want to talk with you about today.
Well, are you going to keep me waiting to find out what it is you want to talk about, or?
Sorry, I guess I'm a little bit out of practice. How about I let Ben Brown, a researcher at IBM Quantum, tell us instead?
We have to build a quantum computer out of something, and lots of people have lots of different ideas about that. I work for IBM, and there we're trying to make a quantum computer out of superconducting qubits, but other people have ideas on using, say, trapped ions, for example, or photons to encode qubits, which are, processing the quantum information of a quantum computer. But, well, common to all of the approaches is that the qubits that we can make in the lab, they're never perfect. And sometimes you set them in some state, and through no fault of your own, the environment or just some miscalibration or something will flip that qubit to the wrong state.
So what? Don't classical computers also have issues with errors?
They do, but the way classical computers are built actually helps ameliorate them.
By storing a bit in the direction a magnetic field is pointing, you've asked a whole Avogadro's number many of atoms to all agree to point in the same direction, or all up or all down. And if some of those bits try to flip, well, you can think of these atoms as tiny little magnets that suddenly get pulled back to align with the other magnets. So they just sort of fix themselves.
Whereas the way quantum computers are built may actually make errors harder to handle.
Classically, we just have bits that flip up and down. But when we talk about qubits, qubits are, this is a quantum way of storing information. And you can think of them as a bit where you can have a 0 or a 1 state, but you can also make superpositions of the states. And this is something that classical computers don't have, which is partly why quantum computers are different. And we exploit the fact that they can make superpositions of states to do calculations. So qubits, because they're bits that can also live in a superposition, they can flip like the classical bits of a regular computer, but there are other errors that can occur as well.
These errors can lead to losing information in the quantum computing system. Or instead of thinking of losing information, you can think of it as introducing noise.
Okay, so when I talk about quantum noise, it usually refers to things like not being able to carry out a quantum gate perfectly.
Ooh, a new voice. Who is this?
So my name is Yihui Kwek. I am a postdoc at MIT, and I am an incoming assistant professor at EPFL, École Polytechnique Fédérale de Lausanne, in Switzerland.
Yihui started with the two different types of noise that appear in quantum computing systems. The first is called T1, or amplitude dampening noise.
For amplitude damping noise, let's say that you are computing with some atoms with two energy levels. So T1 noise is noise that kind of encourages an atom to go from an excited energy level to its ground state. Of course, there's also transitions from the ground state to the excited state, but they don't happen as often as in the other direction. So that's T1 type of noise.
Okay. So like going from a 1 to a 0 in a classical computer.
Exactly. And there is a T2 type of noise as well.
For T2 type of noise, that's kind of similar to what theorists understand to be depolarizing noise. So yeah, that's just when your atom is gradually kind of like becoming more classical, let's say.
And what does it mean for the qubits to start acting classically? Is the qubit playing Chopin?
Well, in this case, it means that instead of maintaining their superposition of different probabilities of 0 or 1, they're replaced by what is known as the maximally mixed state. The maximally mixed state is kind of like the quantum analog of uniform probability distributions. This means that the probability of every possible state would be equally likely. And so when we talk about this noise replacing a qubit with the maximally mixed state, that's bad because the maximally mixed state is non-quantum and doesn't contain enough information for you to do any sort of computation. So the fact that this noise has some probability of replacing the input qubit with this rather useless object means that the noise is kind of like decreasing the amount of information in whatever it sees.
Okay. Yeah, decreasing the information to a state where it's not possible to compute is clearly a big problem. Now, I know you wouldn't have started us down this road if there wasn't any way of dealing with these errors and noise.
You know what? You should be a podcaster with that sort of insight. And, of course, you're right.
Error correction and error mitigation are two different ways of kind of correcting for the effects of the noise.
Great, but what do they mean?
Let's talk about error correction first.
With quantum error correction, you are constantly monitoring your circuit to see if any errors have arisen. And if any errors have arisen, you measure it, you realize that there's an error, and then you do an operation that corrects the error.
Error correction has been an important part of computing and communications for a long time. And mathematicians have created many tools and algorithms that can help identify and correct errors for traditional systems. The first error correction code was developed by Richard Hamming in 1950 and used 7 total bits, where 4 bits contained the message and 3 were there to help detect and correct the errors. Similarly to this groundbreaking work by Hamming, quantum error correction also relies on multiple qubits working together.
But error correction is all about how we can take, several of these qubits and make them work together in such a way that collectively they can protect one logical qubit of our quantum computer.
More specifically,
we make what we call an error correcting code, which is where we use several of these slightly noisy qubits, and then we make, we call them stabilizer measurements or checks. And these are quantum measurements we make on all of the physical qubits. And these checks are supposed to always give us a certain outcome. If we make this measurement, they're always supposed to tell us 1, for example, right? But if we measure them and they give a different answer, we can detect an error and we know we have to do something about it.
Well, that sounds great. So, problem solved?
It can't be that easy, or this would be a short episode.
Okay. Well, can't blame me for trying to set you up.
No, I can't. And you have done a good job, because this error correction isn't perfect.
The principle behind error correction, though, works that if we spend more and more on physical qubits, the failure rate should go down. The failure rate is the likelihood that, the error correcting code doesn't protect the logical information.
Which sounds great, except that qubits are very expensive to produce, which means that Ben and many, many other quantum computer scientists are looking for something very specific.
We're trying to find the best possible code with the smallest possible failure rate, with that uses the least number of qubits.
I don't know if many people would be happy with a failure rate above 0 for most of their computational needs.
I know, which is why it's good that the quantum computer theorists have a theorem to fall back on.
We have a celebrated theorem. We always write it in papers that it's a celebrated theorem that we call the threshold theorem. And that tells us that, it tells us that quantum computing is scalable at all with noisy qubits. Like, we assume that the qubits are definitely noisy, and we assume some things about how the environment will act on those qubits, that, maybe the noise acts locally on, it doesn't like correlate and act on 2 qubits that are far away from each other. Like, otherwise we're in a real mess. But assuming, certain sensible things like this, and that our qubits are fairly good, so the noise on those isn't too bad. What it says is we can make the code bigger and bigger and bigger, and the failure rate will get smaller and smaller and smaller until essentially you have a perfect logical qubit. If you're willing to spend, if you're willing to buy enough qubits, you can make a logical qubit as good as you like.
And what is this threshold that the theorem is named after?
I asked Ben that same question.
The threshold is a number, like how noisy can the qubits be, and such that this scaling is still working well. So if you're below this threshold rate of error, then your qubits are good enough that you can make your code bigger and bigger and bigger, and the logical error rate will go down really, really fast, and you'll have a nearly perfect qubit with a sensible number of physical qubits.
So what about the qubits being made today? How does their noise compare to thresholds being aimed for?
It turns out that they are getting very good.
And it's an exciting time to be in the field, because now we're really seeing qubits are below this threshold, and we're seeing what we call break-even results, where the qubits that we produce on these quantum error correcting codes are better than the qubits that we use to make the error correcting codes.
But so far we've only talked about how to detect errors. What does Ben do after he knows there's an error?
Hold your horses. Ben was about to get there.
Well, maybe the standard option these days is to say we're going to correct the error. We're going to look at the checks that went wrong, and we're going to make an educated guess on what's gone wrong, and we'll try and fix it. But another thing we can do is we just say, well, we detected an error. Let's throw it out and start again.
And in order to make this decision, they use what's known as a decoding algorithm, which is a classical computing algorithm which sits on top of the quantum computer.
So what's happening is, down here we have the qubits, and they're nice and cold. and we're doing the check measurements here to try and spot the errors, we take that information and we send it to the classical computer, which is running the decoding algorithm. And the decoding algorithm looks at what checks have flashed and what checks have not flashed and, given a no error result. And then it decides how to fix it.
Which gets us to work Ben did with Samuel Smith and Stephen Bartlett on how tolerant these decoders should be with these errors.
Wait, what does tolerance mean in this case?
Well, here's an extreme example Ben shared with me that I found helpful when thinking about it.
You could try something like this. Like here's like the most intolerant version of decoding, where the decoder, the quantum chip looks at all the information that comes out. It says, did any of my checks register detecting an error? And it says, if any of them registered, we throw it out, we're done. But you don't always want to do that, especially because as your quantum computer is getting bigger and bigger and bigger, you have to make more and more checks. And like eventually, just, it's not difficult maths, right? Like eventually the probability of seeing a check is going to go to 1, right? That's the way it is. But, it's still maybe a good idea not to try and correct everything.
And they built this idea of tolerance into their decoder?
They did, which means they can vary the probability of error that they are willing to risk, which is important as that maximally intolerant decoder has a big limitation.
It's going to work really well because we're going to throw out anything anytime we might have seen an error, but we throw out a lot. And it might just take the age of the universe before you get the perfect sample where definitely no errors happened.
Yeah, I guess never finishing any computation at all, a la the spinning wheel of doom, would be worse than an error.
For sure. And the decoder they built tries to ride that line between performance and errors.
So what our decoder does is we interpolate this number between the completely tolerant case and the completely intolerant case, saying, we're willing to, let the decoder try a bit, but if it's looking a little bit too close, then we're not going to keep it. And we can quantify that gap between how close we want it to be. And what we see is we can improve the error correction performance a bit by throwing out some samples, but not too many samples.
And it works.
The logical error rate improves on a fixed number of qubits. And as I said, qubits are expensive. And we're going to take a little bit longer, but we're not going to take the age of the universe. So this is a very useful tool for improving a quantum computer to make a decoder that's a little bit intolerant to bad cases.
Wow. Okay, that's great.
It gets even better, as they showed that with a well-designed scheme for choosing whether or not to throw out potential errors, this choice is referred to as post-selection. There is another important threshold.
What we found was if you choose your post-selection scheme a bit more modestly, the way I was describing before, there comes a point below the error correction threshold. There's another threshold where your physical qubits, if your physical qubits are at least this good, your post-selection actually gets better and better and better as well. So as you make the code bigger and bigger and bigger, with a sensible post-selection scheme, the likelihood of your computation succeeding and not being thrown out by the intolerant decoder improves. So the time it takes goes down the bigger you make your quantum computer if you're using these post-selection tricks to improve your logical error rates.
You did bring up that there were 2 different approaches to handling the noisy qubits, though, didn't you?
I did. The second is called error mitigation, and we will hear about that from Yiwei soon. But I want to tell you about a really interesting error correction method that she shared with me first. It's called the quantum refrigerator construction.
Ooh.
So the quantum refrigerator construction goes back to this issue that we've been talking about for a while, which is the issue of doing intermediate measurements. With error correction, intermediate measurements are necessary because you need to know when an error has occurred and to correct it. But the quantum refrigerator construction is a way of doing error correction without intermediate measurements.
But why do we care about these intermediate measurements?
Because we're dealing with quantum states. And one thing that I definitely know about quantum mechanics is that in order to measure a quantum system, you have to collapse wave functions. The wave function basically is what describes all the possible states of the system and the probability of the system being in any of those states. When one makes that measurement, the wave function collapses into one of those many states.
Of course. But this construction somehow works around this?
Precisely. But it requires a lot of qubits, and those qubits have to be noisy in the T1 or amplitude dampening, not the T2 way.
Okay. So how does it work?
The details are very technical, but it relies on research from Dorit Aronov, Michael Benor, Daniel Gottesman, and Avinathan Hasidim about error correction without collapsing quantum states and leveraging how amplitude dampening noise primarily takes qubits and flips them from 0 to 1 states.
Just by allowing the noise to idle on the qubits, eventually you're going to find that like noisy qubits are going to be converted to qubits that are very close to the all zero state. But the all zero state is exactly what was needed to facilitate this coherent sort of error correction that doesn't require intermediate measurements.
Which really means...
So the quantum refrigerator construction combines these two ideas and says that if you have a certain kind of noise in your circuit, then your noise could actually be helping you instead of obstructing you.
Ooh, that is so cool.
Maybe even as cool as your fridge.
Boo, Sam, come on.
Sorry. Will introducing the idea of error mitigation help make up for that terrible joke?
Yeah, it'll be a start.
Good. Let's hear some more from Yue then.
With quantum error mitigation, there's no constant monitoring of your circuit. What you do is you run the entire circuit or variants of the circuit that you hope to run. And then after the entire circuit run has concluded, you look at the output of the circuit run, and then you try and do some statistical inference process to figure out what exactly was the noise that occurred during the run of the circuit, and then you try and correct that in classical post-processing.
Ah, another method that doesn't require intermediate measurements.
Exactly. In fact, the error mitigation approach was developed due to the cost of both the constant monitoring and of the qubits required for quantum error correction. That is not to say that mitigation doesn't have its own downsides.
You pay for this convenience. And one of the ways you pay for it is that you have to run your circuit many, many times. And if in order to achieve the same level of correction, you need to run your circuit too many times, then at some point, you don't really save too much by doing quantum error mitigation, because you're kind of like, paying for it in terms of how many times you need to like employ a quantum device, and it could potentially just like be a huge time sink.
In fact, Yue has shown in her research that there are some cases where the number of runs is incredibly unwieldy.
We constructed circuits that require a super polynomial number of circuit runs in order to be error mitigated.
The specifics of what super polynomial means isn't important. Just know that it means more runs than would be in any way practical. But this specific case was constructed to be really hard. And there are many cases where error mitigation is practical.
But with all these different possibilities, how can quantum computer scientists know which way to go?
I'm sorry, but the answer really is that it depends.
With quantum error mitigation and quantum error correction, you can think of them as being on two ends of a spectrum, where you can think of the scale as being like what amount of quantum control you need or quantum resources. So quantum error correction is something that requires a large amount of quantum resources. It requires intermediate measurements, for one. And with quantum error mitigation, it's kind of a quantum budget-friendly way of doing error correction.
So if you have access to a lot of qubits or a lot of money, then maybe error correction is the way to go. But if you are more resource-strapped, maybe you will lean towards mitigation. Though some research is now showing that the two methods can be used in tandem as well. And while the specifics are not quite clear yet, Yue does think that good progress is being made with errors in quantum computing.
I think right now we are still at the stage where we are kind of getting very close to to good error correction, and we should probably turn our attention to finding more and more algorithms for quantum computers. And once we have done that, then we can think about whether any of these algorithms can actually bring some commercial value.
And there's definitely one thing that quantum computer scientists have had and continue to have on their side towards achieving these goals.
The amount of attention that quantum computing has received in the press is something that I'm very grateful for, because I think a lot of this has also led to greater investment in quantum computing, and that has led to the research that is making error correction progress so fast today.
Press attention that we are contributing to right now. I guess we can now start calling ourselves quantum computer scientists too, with all this help that we've provided in progressing the field. I'll add it to my LinkedIn right away.
You go right on ahead. While I definitely know more than I did before starting reporting this episode, I in no way am conversant enough to call myself a quantum anything. But maybe I will feel different after sharing a novel application of qubits.
And when will you share that?
After the break, of course.
Of course.
Have you ever wondered what goes on inside a black hole? Or why time only moves in one direction? Or what is really so weird about quantum mechanics? Well, you should listen to Why This Universe. On this podcast, you'll hear about the strangest and most interesting ideas in physics, broken down by physicists Dan Hooper and Shama Waxman. If you want to learn about our universe from the quantum to the cosmic, you won't want to miss Why This Universe, part of the University of Chicago Podcast Network. Excited to hear about a very different application of qubits?
You know it.
Well, before we do, I need to ask you a question. Do you know what dark matter is?
Does anyone?
Right answer.
Well, the short answer is that no one knows what dark matter is. We have overwhelming astrophysical and cosmological evidence for this mysterious fluid, this mysterious matter that permeates, as far as we can tell, throughout the universe.
I do want to know whose voice that is. But first, I want to ask about this overwhelming evidence. What is it?
We can look at how galaxies spin, measure the speed of the stars orbiting the center of that galaxy, and say there's not enough from all the stars that we can see, all the gas and the dust that we can measure with our optical instruments. We would not see enough mass to hold those stars on orbits in that galaxy.
Since our star and our galaxy don't seem to be spinning apart, that seems like rather great evidence. Okay, so who was that?
That was Dylan Temples.
I am a Letterman postdoctoral fellow at the Fermi National Accelerator Lab, and I work on dark matter direct detection and kind of the intersection of dark matter direct detection and quantum information science.
Ooh, I know Fermi Lab. They're one of the Department of Energy national labs and do a lot of particle physics, right?
Right. They smash very small things together with very large accelerators. They run the Deep Underground Neutrino Experiment, and they are trying to detect dark matter with the help of people like Dylan.
I know scientists love detecting things, but why dark matter? It seems to be doing its job and doesn't want anything to do with us and the rest of the visible universe. So why try to detect it?
I asked Dylan a similar question.
One, compelling in the sense of it is very important to the story of the cosmological evolution of the universe. How did we come to be here in the first place?
Wow. Understanding our cosmic origins. That's pretty deep. But are there also other questions motivating Dylan?
There are a number of properties of the dark matter that make it a challenge to detect in the lab. And so to get there, you need to develop new technologies and more powerful, more sensitive technologies to help you get to the sensitivities that you need to be able to potentially detect whatever the constituent particles of the dark matter may be. And so one of these areas is quantum sensing that is recently taken off to look for dark matter in the lab.
So while trying to figure out this big question from basic science, they're also creating a lot of cool technology that could be useful in other areas.
Just like how NASA helped contribute to things from vascular bypass surgeries to firefighting to cochlear implants to better mattresses. Basic science research has led to so many of the things that we use in our daily life that we would be here for days listing them all.
And I don't have that sort of time. So how about instead we talk about the specifics, what it means to detect dark matter?
Okay, that we can definitely do.
But what we want to do is, from a particle physics point of view, understand what are the particle constituents of that dark matter, what are the little pieces that make up these large-scale dynamics that we're seeing.
And the way they are trying to sense this dark matter is through the use of qubits, which of course begs the question.
So why might you even consider using a qubit for detection of radiation or dark matter in our case?
That is a very good question.
Yes, it is. And to answer, we need to talk a little bit more about qubits.
Anything where you have two energy states separated by some amount of energy can behave like a qubit.
Which does offer quite a few different options.
There are many things that can be used as qubits. So you can use atoms, you can use trapped ions, all of these things that have different energy levels as a qubit. What our group focuses on are superconducting qubits.
These superconducting qubits are circuits that have been chilled to within 1% of 1 degree of Celsius above absolute zero. So ridiculously cold. And then if you send in a small amount of microwave photons, you can get the qubit to change from one state to the other. In other words, it will exhibit quantum behavior. And once you have your qubits,
if you can completely isolate your qubit, your two-level system, it will last indefinitely. It has no interactions with the outside world. And so you can put it in some state and it'll just stay there.
And this is the start of the answer to why they are using qubits for dark matter detection. The rest of the answer starts with how it is impossible to fully isolate anything, and continues with the fact that
these qubits are very, very sensitive to interactions with their environment.
Which, when combined with what we already know about how easily qubits are impacted by noise, leads us to,
if you have something that is sensitive to very, very small changes in the environment, you can potentially use that to detect very, very weak or very, very rare signals that might be interacting in your chip.
Wait. Are you saying that qubits being so easy to cause errors in, the exact thing we spent the first half of this episode talking about, is the reason they're able to be used as hypersensitive detectors?
How about we ask Dylan? So you're essentially using the fact that quantum computing is really, really hard to leverage the thing that quantum computing folks hate to do your work?
Yes, exactly.
I love this. I guess there really is a silver lining everywhere.
Seems so, but Dylan doesn't see these approaches as being in opposition.
We want to understand the same things and then optimize in different directions. So we want to understand in our group, how does our qubit react to radiation? And taking that information for the quantum computing side, they want to engineer more robust qubits to ignore these effects, whereas we want to maximize the information exchange with the environment in certain ways that we can control.
So they have these qubits. How do they actually try to use them to find dark matter?
Well, first they have to try and isolate them as much as possible. In this case, that means burying them deep underground to try to shield them from as many interactions as possible. Thankfully, while the Earth will absorb the majority of the particles and radiation,
the things that we care about, dark matter, doesn't see the rock as a big burden. It's equally as likely that a dark matter particle will interact in the rock as it is in our detector.
Then once the qubit detectors have been triggered, scientists have to determine if what caused the interaction was dark matter or not. So they have to compare the information from the qubits to models they have developed for what they expect non-dark matter interactions to look like and what they would expect dark matter interactions to look like.
Okay, this is what my standard model background looks like. This is what I expect my dark matter to look like. Then I do my experiment and I say, is my result statistically compatible with the background, or is it statistically compatible with the background plus a little bit of dark matter? And so it's all about understanding on a large scale what signals you expect to see and what a dark matter signal should look like.
Which is all really fascinating, except there's a big problem.
Uh-oh. But I know you, Sam. I totally saw that one coming.
I guess I can be a little predictable, which is not true for dark matter. So it makes sense that
we don't know the mass of an individual dark matter particle.
And let me guess, there are some possible masses for dark matter that qubits can't detect?
Before we get to that, we should probably dig a little deeper into how little we know about the mass of dark matter particles.
I'm scared now, but okay.
And so there are some very loose constraints on what that mass could be, and that spans about 50 orders of magnitude.
Oh my gosh, what? I was right to be scared. 50 orders of magnitude? I have no idea what sort of mass range that could possibly mean.
Neither did I. So I had Dylan do some quick calculations.
So 50 orders of magnitude is quite hard to wrap your head around. But the ratio of the heaviest dark matter to the lightest dark matter is 1 with 50 zeros behind it. That is roughly the same ratio as the mass of the Milky Way galaxy compared to the mass of an E. coli bacterium. And so these are enormous scales. And so depending on where you're looking in that 50 orders of magnitude, you have very different phenomenology, different ways of that dark matter manifesting itself in the lab. And the technology that you need to look for dark matter that's very heavy is far and away different from the stuff that you need to look for the ultralight stuff.
If the dark matter is on the heavier side of things, the qubit detectors have a chance of working. But for the ultralight side, a different approach needs to be taken, one that relies on some pretty mind-blowing physics.
It could induce time-dependent fluctuations in the fundamental constants of nature. So the constants of nature become no longer constant. You get a very, very small correction to the mass of the electron and to the fine structure constant.
Huh? So if dark matter is ultralight, then it could cause things that we have always relied on to be unchanging everywhere, like the speed of light, to now not be constant?
That's right, but only for a short period of time and only locally. Thankfully, what changes can be measured.
If you have something that is very good at measuring the mass of the electron or the fine structure constant, you can start to be sensitive to these very, very small oscillating corrections. And that is where MAGIS comes into play for the search for dark matter.
MAGIS 100, otherwise known as the Matter Wave Atomic Gradiometer Interferometric Sensor, is just such a measurement tool, and one that again leverages quantum mechanical behavior to do its sensing. They start by cooling down atoms a factor of 1,000 more than the superconducting qubits.
This is a measure of kinetic energy, and it's not really a macroscopic temperature. You can't put your finger on it and go, boy, that's cold. It just means I've sucked all the energy out of these atoms.
And at temperatures and energy levels like this, thanks to the quantum wave-particle duality, objects will start to display wave-like behavior. In particular, they cool down strontium-87, an atom that is popular for building highly precise atomic clocks.
And so it has these two clock states, the ground state and one of the excited states that we care about. And so we drive transitions between those things. And the interference pattern that you get out at the end is dependent on the energy difference between those two energy levels. That energy difference depends on the mass of the electron and the fine structure constant.
So if MAGIS sees a change in those constants,
You got it.
The output of our interference measurement will change in time, and it will oscillate at the same frequency as the dark matter. And so that is one of the ways that you can look for a very specific type of dark matter or specific class of dark matter models with this matter wave interferometer.
And
what?
And does Dylan think one of these will actually work?
Let's differentiate between work and fine dark matter. So these experiments, they will work.
But working doesn't mean detecting, does it?
It does not. But that doesn't mean nothing will be learned.
So we are in this business of, at least in the dark matter sense, measuring zero better and better.
It's also worth remembering that these detectors will have an impact well beyond dark matter research.
Qubits have been around for a while, but we're still far away from building a real quantum computer. And the more that we can understand about the noise sources and the backgrounds that influence the information loss in quantum bits, helps us get towards building a realistic, large-scale quantum computer.
Of course. And I bet that MAGIS will also lead to breakthroughs that industry will be salivating over. But what if they really detect something?
Dylan has some thoughts about that.
What would it mean if we actually detected dark matter with one of these things? Well, someone gets a Nobel Prize. Probably not me, because I just built the thing. Probably whoever thought about the model that we discovered.
And no matter if they can conclusively say that something they detect is dark matter, any signal could be helpful when searching such a wide set of possibilities.
Right now, we're searching 50 orders of magnitude. Once we see something that might be a signal, we can start to focus effort on the technologies and new technologies, different technologies that would be sensitive to dark matter in that mass range, and really start to suss out all of the different expectations that we have for what dark matter should do, and see that we're observing that in different systems, different technologies. And I think that's really exciting.
Yeah, the analogy of a needle in a haystack doesn't even come close to this challenge. Just being able to narrow it down to looking for something between huge ranges like bacteria and human or solar system and galaxy would be a massive leap forward.
I mean, I bet Dylan would like to get closer to, say, between cat and human, but you aren't wrong. Do you still feel like we should call ourselves quantum computer scientists?
You know what? Maybe I did jump the gun earlier, though I am going to call myself a quantum podcaster now.
Oh,
so
hell yeah. Me too. Don't forget to check out our show notes in the podcast episode for more Ben, Yue, and Dylan, including links to their work that we discussed on this episode.
And if you like the show, give us a review on Apple Podcasts or Spotify or wherever you listen. By rating and reviewing the show, you really help spread the word about Carry the Two so that other listeners can discover us.
And for more on the mathematical research being shared at IMSI, be sure to check us out online at our homepage, imsi.institute. We're also on Blue Sky at imsi.institute, as well as Instagram at imsi.institute. That's IMSI spelled IMSI.
And do you have a burning math question? Maybe you have an idea for a story on how mathematics and statistics connect with the world around us. Send us an email with your idea.
You can send your feedback, ideas, and more to sam@imsi.institute. That's sam@imsi.institute.
We'd also like to thank Blue Dot Sessions for the music we use in Carry the Two.
Lastly, Carry the Two is made possible by the Institute for Mathematical and Statistical Innovation, located on the gorgeous campus of the University of Chicago. We are supported by the National Science Foundation and the University of Chicago.
He's like, where's your chalkboard? All right, I'm ready.
Literally didn't know that was possible.
Absurd. Lies.
I can go all the way down here and go real smooth.
Your failure is my joy. What is happening?
Oh, I immediately forgot the pronunciation. Yeah.
So sorry. That was gross. That cannot go in the outtake. Oh, are you gonna talk? Are you gonna lose it again? Mathematical.